Scientists did not go to the edge of the solar system looking for new life forms. They went to the bottom of the Pacific Ocean, and during one routine deep-sea survey, instruments began detecting something that should not have existed at all. Living organisms were found thriving inside solid rock, sealed in complete darkness, with no connection to the surface world above them for over 1 million years. And the deeper scientists looked beneath the seafloor itself, the stranger everything became. For decades, the deepest layers beneath Earth's ocean floor were considered scientifically irrelevant. The assumption was simple. Once you go deep enough into rock and sediment, conditions become so hostile that biology simply stops. No oxygen, no nutrients, no light, no life. That assumption collapsed when researchers began drilling. In 2012, scientists participating in the Integrated Ocean Drilling Program bored cores deep into ancient marine sediment on the floor of the South Pacific Gyre. The South Pacific Gyre is the most nutrient-poor region of the open ocean, a biological desert so extreme that almost nothing lives in the water above it. Scientists expected the sediment beneath it to be completely sterile. Instead, they found microbial communities living in sediment 100 million years old, sealed beneath the seafloor with almost no available nutrients and almost no available oxygen. Not fossils, not chemical traces of past life. Living organisms, dormant but alive, breathing at rates so slow they consume almost no energy at all. The cells appeared to survive in extreme slow motion, maintaining their structure and persisting across timescales that dwarf the entire evolutionary history of complex life on Earth. The researchers described the discovery as finding life at the absolute boundary of what biology should be able to do. Then the follow-up results made the first results look almost ordinary. When scientists analyzed the metabolic activity of the microbes more carefully, they discovered these organisms had found ways to extract energy from chemical interactions between minerals in surrounding rock and trace amounts of water, molecules split apart by natural radioactive decay in the sediment. Radioactive decay in ancient rock was feeding microbial communities cut off from the surface world for tens of millions of years. That single mechanism, life sustained entirely by the chemistry of decaying radioactive minerals buried in seafloor sediment, rewrote the scientific understanding of where biology can exist. Because radioactive minerals are not rare, they are present in the crusts of every rocky planet and moon in the solar system. If life can survive on Earth powered by nothing but radioactive decay and mineral chemistry, locked inside rock for millions of years with no sunlight and no connection to the surface, the question of where else in the solar system this could be happening becomes very difficult to dismiss. Scientists then turned attention back to a problem that had been waiting for a direct answer. For years, researchers had known that hydrothermal systems exist not only at spreading ridges on the ocean floor but potentially deep within the rocky interiors of icy moons. Europa, the fourth largest moon of Jupiter, has a confirmed global ocean beneath its frozen surface. Enceladus, orbiting Saturn, is actively venting material from its subsurface ocean through cracks in its south polar ice shell. Both worlds have liquid water, internal heat sources, and rocky seafloors that interact with that water over geological timescales. The same three ingredients that appear to sustain microbial communities in the deep sediment of Earth's ocean floor. Genetic analysis showed they were closely related to microbial communities found in far less extreme environments. Ordinary bacteria and archaea that had gradually adapted to increasingly challenging conditions over millions of years. In other words, extreme subsurface life on Earth did not require special origins. It required only time and the right initial conditions. The ability to survive at the edge of biological possibility appears to be a default outcome given enough time and enough pressure. That finding has direct consequences for how scientists think about the history of Mars. 4 billion years ago, Mars had liquid water on its surface, a thicker atmosphere, and active geology. Life, if it arose during that period, would have had hundreds of millions of years to adapt to worsening surface conditions as the atmosphere thinned and liquid water retreated underground. The subsurface of Mars today is not hospitable by surface standards, but by the standards of the South Pacific Gyre sediment, it may not need to be. Liquid water likely still exists deep underground at Mars. Radioactive minerals are present throughout its crust. The chemical energy sources that sustain life in Earth's deepest sediment almost certainly exist beneath the Martian surface. Scientists now take this seriously enough that it shapes the design of future missions. The European Space Agency's ExoMars Rosalind Franklin rover, designed to drill 2 meters below the Martian surface, specifically targets subsurface material because the surface itself is too thoroughly sterilized by radiation and oxidizing chemistry to preserve any biological evidence from the ancient past. If life ever existed on Mars, its best preserved record is underground. And if any life persists today, it is almost certainly underground. The discovery in the South Pacific Gyre sediment is the closest Earth analog for that possibility ever identified. But the strangest part of the story has not yet been told. When the research team returned for follow-up sampling, they found something the original expedition had not detected. In cores taken from sediment at the transition zone between ancient deep sediment and the overlying water column, they identified a chemical gradient, a boundary layer where conditions shifted from the nutrient-poor sediment environment to the slightly richer water above. Living along that gradient, in a zone only a few centimeters thick, were microbial communities with measurably higher metabolic activity than anything found deeper in the sediment. Occupying the one location where they had access to 2 slightly different chemical environments simultaneously, using the difference between them the way a battery uses the difference between its 2 terminals. Chemistry generating electricity, electricity sustaining biology. The same principle that powers every living cell on Earth, expressed at the absolute minimum scale of what biology can manage. When researchers modeled whether similar gradient zones could exist in the subsurface of Europa, the answer was yes. Anywhere that the chemistry of a rocky seafloor interacts with liquid water above it, gradients form. And wherever gradients form, the conditions that sustain microbial life in Earth's deepest sediment could in principle operate. So when the next deep space mission drops instruments into whatever ocean lies beneath Europa's ice, it will carry a new and specific question shaped by what a drilling ship found at the bottom of the Pacific, not whether life requires sunlight. That question was answered near hydrothermal vents decades ago, not whether life requires nutrients. That question was answered in the South Pacific sediment. The question now is simpler. Is there a gradient? Is there a boundary between 2 slightly different chemical environments? Because wherever that boundary exists, anywhere in the solar system, life on Earth has demonstrated that the basic conditions for biology to persist are present. The ocean floor is no longer just an unexplored part of Earth. It has become the most important laboratory in the search for life beyond it, and every core sample drilled from ancient seafloor sediment, every organism found surviving on radioactive chemistry at the edge of biological possibility, brings that search one calibration closer to the answer it has been building toward for decades. Are we alone, or have we simply not drilled deep enough yet? Thanks for watching. Don't forget to subscribe for more.